Sarah is working at the University of Manchester with Aurora Cruz-Cabeza, and there's also Roger Davey. And strictly speaking, I'm also her supervisor, although I don't profess to be an expert in her particular area of domain. And she's going to give us a presentation today called "Is It Unusual to Be Unusual?" Looking at conformations. Over to you, Sarah.
Hi everyone, thank you, Jason. So I'm here to talk to you today about my work. Is it usual to be unusual? There we go. I'm gonna start by introducing myself because I can't do it in person. So this is me here and my supervisor Aurora, and we're part of the CAPE group at the University of Manchester. And as Jason said, he's now my supervisor at CCDC. So the majority of my presentation today will focus on work that's gone into my first paper, which was published at the beginning of the year, and then I'll move on to some of the experimental work that I've been able to do since returning to the lab. So first of all, why do we care about molecular conformation? In the solid form, different conformations can affect a variety of properties. For example, in polymorphs, Roy is a very common example, known for its red, orange and yellow polymorphs, and these relate to different conformers. So the red-orange conformers are in this conformer well, and the yellow polymorphs are in this conformer well. And ritonavir is also a well-known example of a conformational polymorph which disappeared after the discovery of a more stable form, which then compromised the solubility of the drug, resulting in it being withdrawn from the market and being reformulated. So two important concepts to note when talking about conformations in crystal structures are conformational adjustment and conformational change, which were defined by Aurora and Joel Bernstein in their paper on conformational polymorphism. So these can be identified by obtaining a gas phase potential energy surface of a molecule. And so two conformers are related by conformational change, and they have to go over the potential energy barrier in order to convert. And you can also have that when a molecule is in a crystal, its conformation can adjust slightly to improve intermolecular interactions, and then this is referred to as conformational adjustment. So the reason we're interested in molecular conformation is its effect on crystallization, and conformationally flexible molecules have a greater number of structural options and many conformers available in the solution. And this means that the right conformer needs to be selected during crystallization, and this could result in conformational change, which could add a limiting step to crystal growth. So first, I'm going to discuss my research looking at unusual torsions in the CSD, and then my new classification of unusual, which incorporates the concepts of conformational change and adjustment, my selection process for the thresholds used, and then implication statistics of this definition. So the CSD conformer distributions have been shown to be a good guide for the corresponding gas phase potential energy surface, where the torsion angles associated with high strain energy tend to be very unusual in crystal structures. So if you've used Mogul, it defines unusual torsions as being unusual when less than 5% of the distribution is within 10 degrees of the observed value. And so in my work, I classify unusual structures as being unusual if they have at least one unusual torsion in the structure. So this structure on the right has one unusual torsion here, so therefore it's an unusual structure. So then looking at the number of structures containing at least one unusual torsion, we found that for single component systems, around 15% have at least one unusual torsion angle. And then this has been repeated with other solid form types which show similar frequency of unusual torsions. So we then also found structures which are found in local energy minima, and so they're not necessarily conformationally strained. And this led to us wanting to be able to incorporate conformational change into our definition. So if we then move on to my new classification, which incorporates conformational change and adjustment, I've used a regression to fit a non-periodic function to the distribution in order to identify the unique peaks. And so then unusual adjustment we've determined by looking at the population of the observed bin in green and comparing it to the peak that it's in blue. And that gives us p-adjust. And then unusual change is determined by comparing the population of this observed peak, so the whole of this blue peak, with the red peak here. So during this investigation, we found that the CSD distributions retrieved by Mogul aren't always representative of the query torsion, which we found to be especially important when we were looking at conformational change. So two key factors that we found were if the rotatable bond is constrained by a hydrogen bond, so like here, this torsion angle is fixed in place by this hydrogen bond, or the torsion angle is within a cyclic ring, which also kind of holds it in place. And these are shown in this plot. So the hits constrained by a hydrogen bond are shown in yellow. Green shows the acyclic hits, and then dark green shows the cyclic hits. And so then if you filter for these factors, you end up with a very different distribution. And this torsion angle now looks quite normal compared to how it did here. And so this approach allowed us to classify torsions into 4 categories. So we have unusual adjustment, unusual change, unusual adjustment and change, and normal adjustment. So if we look in all of these cases in detail, so unusual adjustment is when the torsion angle is found at the tail end of the populated peak here. Unusual change, the torsion angle is found in this tiny little peak here, but it's in the most populated bin within that peak. And then here it's both unusual by adjustment and change, as it's found in this smaller peak here and also at the tail end of the peak. And then you can have where there's nothing unusual about it at all, and the torsion angle is very normal and happy. So we wanted to then find a way to kind of meaningfully decide the thresholds we used. And since the CSD distributions have been shown to correspond well to the gas phase potential energy surface, we decided to use gas phase energies to decide these. So looking at adjustment energies, this is the energy associated with the torsion angle adjusting to its minimum. And that helped us to determine unusual adjustment. So here we have unusual adjustment against the p-adjust value, and you can see that there's a clear increase in the adjustment energy, lower than a p-adjust of 0.05, so 5%. And we've then chosen this as our threshold for unusual adjustment. Then to decide the threshold for unusual change, we optimize the crystal conformation to its minimum, and then use the CSD Python ABI in order to change the torsion angle to be the maximum of the distribution, so to 80 degrees here, and then optimize that molecule to its minimum, and then calculate the difference between these two energies to give us the change energy. So for unusual change, the threshold probably isn't as clear as for unusual adjustment, and it was decided that if the ratio of the observed peak to the maximum peak was less than 50%, so if the observed peak was half the size of the largest peak in the distribution, then the torsion angle is assigned as having unusual change. So then what does this mean? We found that roughly 30% of structures using this method have at least one unusual torsion, and this is much higher than what we found from Mogul, but this now also accounts for unusual change, which wasn't previously defined. But this approach also gives us a much more detailed picture of the nature of unusual torsions, because obviously molecules contain many different torsion angles, and these can all be a different type of unusual. So here is a Venn diagram, and it's probably not the easiest to understand. So we found that 65% of our unusual structures have only unusual adjustments. So they only have torsion angles which are unusually adjusted. They don't have any unusual change or anything like that. So then 21% have unusual change. So for this torsion angle, it could either be cis or trans, and it's found in the least populated here. And then you could have the case where you can have a torsion angle that's unusually adjusted or one that has unusual change. So here, this torsion angle is classified as unusual change, and then this one is classified as unusual adjustment. So it's a lot more complex of a picture. So then it's important to note that being unusual does not mean that the conformation is necessarily high in energy. So the torsion angles, the torsions classified as unusual adjustment or change tend to have higher energies, but there's still a significant number of structures that have low energies that are below RT. So it doesn't necessarily have high energies, but there are larger differences in geometry, which I guess can be expected. So if you have unusual adjustment, it's usually adjusted 20 degrees from the center of the peak all the way up to 90 degrees. So there can be some very large adjustments there. And conformational change is generally not observed below 40 degrees, and then these are most commonly found at 90 degrees, 120 and 180. And these tend to be known local minima for torsions involving either two aromatic rings, sp3 hybridized atoms and sp2 hybridized atoms respectively. So in this definition, we found that 30% of structures have at least one unusual torsion, and this definition can give us a more detailed picture of the nature of unusual torsions and help understand their possible effect on crystal growth. And it could also prove to be a useful tool for identifying compounds at risk of conformational polymorphism. And we also hope that the CCDC can help us make this method more accessible to the community and maybe implement it within their software.